So good morning, and so let me begin by thanking the organizers for giving me this opportunity to talk about my work. So today I'll be talking about robustness of Kardar-Parisi-Zhang scaling and isotropic classical spin chain, broken integrability. And this is joint work with Manas and Abhishek at ICTS and Harvard at TU Munich. So the plan of the talk is I will begin by giving the motivation and background behind this work. Then I will describe the model. And finally, I will talk about the results that we have got. Okay. So recently, there has been some interesting works in 1D spin chains where super diffusive spin dynamics has been observed. And in fact, in quantum Heisenberg spin chain, this super diffusive spin behavior, spin dynamics has been observed. And for example, these two studies I have mentioned. And note that this quantum Heisenberg spin half chain is basically integrable and isotropic. Later, in a numerical study, Kardar-Parisi-Zhang behavior was observed for quantum Heisenberg spin half chain. Then in another integrable and isotropic spin chain with larger spin symmetry, the same KPG behavior was observed. And then there has been some analytical studies to understand this kind of super diffusion in the context of quantum models. And very recently, there has been this experiments on quantum spin chains where this KPG super diffusion was also observed. And lastly, there has been some numerical studies on classical spin chains which are integrable and isotropic. This KPG behavior has been observed, and I mean they have been studied in very details. So because of these studies, there is a growing consensus that this super diffusion emerges due to integrability and symmetry. Okay. So before I go on, so let me tell something about KPG scaling function in 1D. So in 1986, Kardar-Parisi-Zhang modeled, studied this stochastic partial differential equation to model nonlinear growth phenomena. And here, H is interfacial height profile, nu lambda d are parameters, and eta is a zero mean Gaussian white noise. And if we consider the slope, which is the derivative of this height profile, we can find an evolution equation for this slope. And this is basically stochastic Burger's equation, which is shown in equation 2. And in 2004, Prahofer and Spohn exactly computed the stationary state correlation for U, which has this nice scaling forms. And since then, this the exact KPG scaling function was observed in this integrable spin chains that I have mentioned. Okay. So now, a natural question which comes with integrability in this spin chains is that what happens to the super diffusion when integrability is broken? Now, there has been recent works, a couple of recent works on quantum models. So in one study by Nardis and others, they studied in perturbative regime for the case of symmetry preserving perturbations, and they have observed super diffusion. And there is another study by Claes et al. Who studied a noisy exchange model, and in the strong noise limit, they found regular diffusion. However, there is no detailed study of various parameter regimes in the current literature. And for these quantum models, there are well-known computational challenges, so numerical studies become very hard. But there exists a strong evidence of classical quantum correspondence, so that it is believed that what we observe for classical spin chains in 1D should also behave in the quantum case. So these questions and these issues and these connections motivate us to consider classical spin models which allow extensive numerical study. And I will describe them now. Okay, so let me now describe the model that we are considering. So we consider a 1D periodic chain of 3-dimensional classical spins of unit length. And this has a Hamiltonian, which is given in equation 4. So note the first part. So this is the integrable part. So this is basically Hamiltonian for integrable Lattice-Landau-Lifshitz model at isotropic point. And for this Hamiltonian, KPG behavior has been found, and this scaling function was also shown to exist in this model. And this HNI is basically integrability breaking perturbation. And for this, we'll consider 4 cases. So first 2 cases are symmetry preserving cases, and the last 2 cases are anisotropic cases. And we'll focus mainly on the first case, but I will mention some results for the other cases. Okay. Okay, so this spins in this spin chain follow the Hamilton's dynamics, which is given by equation 5. And then we'll also define something called local energy, which is given in equation 6. Now, for a conserved quantity, which you expect in this isotropic systems at least, and also in the other cases I mentioned. So we will compute this quantity called connected correlator, which we define here. And we will be interested in the spin correlation, SZ correlation, and also this energy correlation. Okay. And for this conserved quantity Q, we expect that this correlation follows some kind of scaling law. Here F is scaling function and alpha is scaling exponent. And we will also compute mean square displacement to extract this alpha directly. Some important cases are this ballistic behavior happens when alpha is 1, diffusive behavior happens when alpha is half, and KPG behavior occurs when alpha is 2/3. Okay, so in our numerical study, we used Metropolis Monte Carlo algorithm to generate initial conditions at thermal equilibrium at temperature 1. And then we used an adaptive Runge-Kutta method to evolve the system for some time. Okay, so we generated data, and now let me describe the results. So, okay, so for case 1, remember that we have next neighboring interaction, and we have symmetry preserving perturbation. And lambda is strength of the perturbation. So we considered 3 cases. So let's go case by case. So the first row describes results for lambda is equal to 0.1. So this is weak perturbative regime. So in this case, the perturbation has low strength. So so in this case, we find that KPG scaling survives. And when we tried to match with the exact scaling function, we found that it agrees very well with the exact KPG scaling function. So this is nice. But then we increased lambda to 0.5, and the results are in this middle row. And we also find this KPG scaling in this case also. But what was surprising to us that when we increased lambda to 1.5, which is strong non-perturbative regime, in that case also we observed KPG behavior. And and these agreements shown in these results are very good. Okay, this is for spin correlation. But what about energy correlation? So remember that for this perturbative regime, we I mentioned, we observe ballistic behavior for the energy correlation. And this is perhaps a bit expected, because for lambda is equal to 0, that is when there is no perturbation, this energy correlation is basically ballistic. So behavior, some kind of behavior for the integrable case to exist for weakly perturbative case, which is the first row. But for the other cases, when perturbation is a bit strong, then we observe diffusive.
5 minutes left.
then we observe a diffusive behavior. Okay. So then we also computed the mean square displacement for both spin and energy correlation. And we observe the scaling exponents match exactly with the scaling that I have shown earlier. Okay. Now, since this KPG behavior seems to be very robust, and though we have added this perturbation to the integrable part and we have broken integrability, one might suspect that, well, maybe integrability is not broken. So to confirm that integrability is indeed broken, we compute this quantity called out of time ordered correlator, or OTOC, which might be known to many in the audience. So we took two copies, one from the thermal, one copy which we call copy A, and we start from the thermal configurations. And then we considered this copy B, which we took the initial condition for copy A, and we perturbed at the center. And then we evolved the two copies, and then we took the difference, and we defined OTOC in this way. And we computed this for the integrable case, which is lambda is equal to 0, and for the perturbed cases that we have discussed. And we observed that for the integrable case, the OTOC doesn't grow much. But when you consider the perturbed cases, in all cases we see, in all perturbed cases, we see that there is a growth in the OTOC. So we clearly observe that there are signature of chaos from these OTOCs. So the integrability is indeed broken in these cases. Okay. Now we have considered one class of symmetry preserving perturbations, but let us consider a second class of perturbation, which also preserves symmetry. And this case also, for all the regimes, weakly perturbating, weakly perturbative, intermediate, and strongly non-perturbative, in all cases we observe KPG scaling, and also the KPG scaling function matches very well with the scaling functions which you get from our simulations. So this results for this case 1 and case 2 suggests that this KPG scaling is indeed very robust. Okay, so till now we have considered symmetry preserving perturbations, but now let us consider some anisotropic cases. So first is the case 3. So for this we consider XXZ type interaction, and for this we show the results in A, B, and C and D, and we find that there is no signature of KPG behavior in these cases. And in E and F, we show the results for XYZ case, and here also we do not find any signature of KPG behavior. So we conclude that this anisotropic integrability breaking perturbations destroy KPG scaling for spin correlation. Okay, so this brings to my conclusion that so we have found from our numerical study that KPG scaling is very robust if integrability is broken by spin symmetry preserving perturbations. And we expect that this robustness should hold true unless lambda by j, which goes to infinity, which means that the perturbation is extremely stronger than the integral part. And we expect that this should be true for all finite temperatures. And finally, because there is a strong correspondence between classical and quantum systems in 1D, we expect that this behavior should also be observed in the quantum case. So thank you. I will stop here.
Thanks, Dipankar. We can take a couple of questions from the audience.
So you have mentioned that your OTOC grows with time, maybe probably. So it grows forever or somewhere it stops?
Yeah, so this is a nonlinear system.
Yeah.
So the growth will be up to some time, it will stop.
But after that, it will saturate or?
Yeah, saturate. But if we consider the linearized system, then it will grow forever. So linearization I have not shown because it is kind of ongoing, and some, I mean, we have not got results for some cases yet. That's why I have not shown. But for some cases, we find that it is indeed growing.
Thank you.
Yes.
Yes.
So I was just wondering, don't you expect that the KPG scaling is robust because of some universality argument?
For example,
no, because I thought the scaling would be that I thought there are some universality argument, but maybe not. I'm just asking. Like, how do you explain that this KPG scaling is robust?
yeah, so we do not know yet that how to explain this, but it is clear from this that even if integrability is broken, we observe KPG. So there might be some special behavior. So I think we are discussing Manus here. So we are discussing some solitons and all these things. Those things might help us in explaining why we are observing this KPG behavior. So we are currently looking to understand numerically whether indeed those assumptions are true.
Thank you, Dipankar.
Yeah.